view on quantum mechanics, which sort of connected rigorously our methods and our approach to the second chapter. We started discussing some examples now of these alchemical changes as they were done in the literature. And I'd like to proceed today to go further in this regard. And there's this is heavily biased towards research contributions from my group, but in the reviews I give you, where I shared the references as well as the papers I cite, you will find that you will find more references to the field, and it would be it's not true that we are the only ones doing this kind of research. There are multiple groups, and I think I will show some of their work too, but you'd have to go through the literature. So in this course, we cannot discuss all possible contributions. It's not a comprehensive overview of what has been done in the literature. The field is already too large for that. Even though it's not a very large community, there are too many contributions to really give a comprehensive overview in this course. But if you look at the literature, you will see that there are many other groups contributing as well. So let me share the slides where we stopped last week. And as always, right, if there are questions, please don't hesitate to interrupt me. And as always, I greatly appreciate if you can switch on your camera so I get more of the lecture feel. In last week's course, we discussed these alchemical changes, and in particular, we last discussed the growth of an ion in a lithium ion in a box of water, and we discussed how to get from an alchemical derivative, let's say evaluated by a Hellman-Feynman, to the free energy difference between states. Okay, so it's the StatMag expectation value, the StatMag average of the QM average, right? Integrated over lambda, right? So you're averaging lambda, so the alchemical degree of freedom, then you're averaging the configurational degree of freedom, and then you're averaging the electronic degrees of freedom, okay? All right. So you see here again, as you increase lambda here, you see electron densities changing, and these are the electron densities in a simulation box, and I believe they correspond to randomly selected snapshots extracted from the molecular dynamics run at each lambda. And then you see the integrand as a function of lambda. In this case, lambda is the same as the growth of the charge. And so the integral under this curve is your free energy of solvation. And you see here the predicted numbers using density functional theory. There's a comparison from force fields. This is what was shown in the experiment. So as you can see, the experiment has a wider range, but these are different experimental groups, right? So it's interesting, even though it's not possible to really back up any single experiment, clearly the density functional theory-based calculations for various settings. So this is the number of water molecules, 64 is a larger box. Then there's a smaller box, 32, and a smaller box, 32. And for each box, you have a different, no, not for each box, but we have also different number of points at which we did the lambda integration. So if the curve varies smoothly, it turns out that 2 points look nearly converged. So you can see this, these are the 2 points, right? For 64 water molecules, only for 2 points, the integrand was obtained. But then for 32 water molecules here, you see the difference in changing number of water molecules between these two, right? So it's a nearly 2 kcal per mole difference. If you go towards more points, now you have 6 points for the 32 water molecules. So you see these crosses, right? That's what happens if you have 6 points. Your integral here hardly changes, only by 0.3 kcal per mole. So the number of water, the converging your system size, at least at this stage, seems to be more important than converging your lambda integration, the numerical integration. That's what these results would suggest, right? Now, force fields are cheaper, so it's also possible to do 6 points with the force field. But you see the difference then between, if based on this series, you assume that this is something reasonable, right, the 126, then you see going from DFT to force field can give you something like 5 kcal per mole difference still. And so this is often force fields are compared to experiments and calibrated also on experimental numbers and so on. And then they can achieve a very good accuracy, right? Sometimes deviations are reported on the order of 1 kcal per mole or less. But it seems it's unclear if this is not rather due to overfitting than due to having actually a realistic model, right? Meaning that as soon as you would vary slightly the conditions such that they deviate from what you have been fitting to, the force field number would deviate dramatically more from experiment. So already the simple deviation from DFT would indicate something like that. So in terms of experiments, then this is what's sort of on the menu, right? And so we can see that these larger numbers on the order of 34, right? They would be consistent with the force field predictions, while DFT would rather be, note also the larger the box, the smaller this number, right? So DFT would rather support this experimental number than the 37. So this is also remarkable, as you can see, that the experimental numbers deviate this much, right? And you see that this is also sort of an issue that we typically presume that experiments are the arbiter of truth, but actually in many cases there can be severe uncertainties, if not inconsistencies, right? On this scale, it's quite dramatic. For systems, for problems as properties as basic as the hydration energy of lithium ions and water, right? I mean, lithium is a very simple salt, right? Easily accessible. But now, due to its importance in battery technology, it should really be obvious that this is a very important property. It could be, so we published this work in 2009, could be that by now there's a more accurate experimental number out there. I should check that. Anyhow, this is where we stopped last week, and I'd like now to give you one more example of how these alchemical changes, how general they are, and what kind of physics they are amenable to.
Maybe one quick question before on kind of the previous example, or maybe more general, the idea of integrating kind of the derivative over lambda instead of just taking kind of the endpoints. I guess the very naive way to do it would have been to just calculate kind of basically with lambda equals 0, doing the StatMag average, only doing lambda 1, doing the StatMag average, and then kind of taking the difference.
Yes.
But where exactly do I gain something by kind of taking the immediate points and like integrating with the derivative? What exactly becomes so much easier?
So in the limit of your observable changing with lambda only in a linear fashion, right? Then the endpoints suffice. Right?
Sure.
So typically this is not the case. So typically your property will change in a nonlinear fashion as you vary lambda. And so to get a converged estimate then of the resulting change in your observable, you need to also consider intermediate points. Now, recall also, we've discussed this as well. I don't recall if it was last week or the week before. We discussed the proof of the concavity. Right? So you know your function is so from this here, right? From the quantum mechanics. So you have two things, right? The integrand for free energies is the StatMag average of the QM average, right? Mm-hmm. So it could be that the StatMag average sort of counters the QM average and imposes some coincidental linearity, right? And then you might be lucky. I don't want to exclude that, but from purely on the QM level, right? You see that the lack of linearity, the degree of nonlinearity is expressed by these two brackets, this bracket and this bracket, right?
I think that part makes sense. The question is just, why couldn't I just like calculate the free energy kind of with lithium and the free energy without lithium and take the difference and be done?
Okay.
So kind of that probably like super naive question, I guess.
No. Okay, that's a very perfect, very valid question. So we discussed this. Let me go on. We discussed this for the free energy for the melting. Oh, where was this? Where did we have the melting? Okay. So consider this case, okay? Mm-hmm. So what you're suggesting is let's calculate the free energy of the crystal and let's calculate the free energy of the liquid and subtract the two.
Exactly.
Now that's of course that would be the first plausible, and well, it's, yeah, you can call it naive, I guess. It's not really naive, right? It's I would call it brute force, or
okay,
let's call it not smart, right? You're not. So in the sense, it's not the efficient way of doing it, and so one of the reasons is, so the absolute free energy of a liquid is virtually impossible to get. It's not really clear how you can do this, right?
And it's so hard because the number of particles could change, or what exactly makes that so difficult? Because
so yes, so you could do this in, so the absolute energies, right? We discussed this when we went through the composition, right? Mm-hmm. As you change the composition, you're changing the absolute energy of your system. And this is on the order of Hartrees, okay? So you need a really good QM method not to make errors. An error of 1% will get you into trouble, right? So you need super small errors percentage-wise, right? Which means you really need a QM method. And then, so to do, and a decent one for that, and then to do StatMech on that for such a system will be numerically impossible to converge simply, right? So brute force-wise. And so what people then say, okay, is something like this, right? The thermodynamic cycle would produce relative energies, not absolute energies, right? And so that's a very common, yeah, it's not really a trick, right? But it's a very common procedure to exploit error cancellation. So your errors and absolute energies of the two states will be the same, more or less. And so then you argue that all we care about are really relative energies, right? Free energy differences, right? So to just compute is to insist on computing the absolute energies is not a necessity, right? If only you care about free energy differences, right? So that is the common justification for.
But by the same argument, couldn't I say, well, I calculate the absolute free energy of the liquid and I calculate the absolute one of the crystal, and they will both be maybe bad. But hopefully when I subtract the two, the errors will cancel and I get kind of the same cancellation when just taking the differences I get when integrating.
Yeah, that's a good point. I don't think that, yeah. Yeah, so I'm not sure that the cancellation works as well, right? But in principle, that, yeah, that argument has something. So the one additional problem is really that when you yeah, so the main problem is the liquid, really. For the solid, actually, you get decent estimates of free energies. But the liquid's free energy has so many sampling issues that I don't think it's possible. But yeah, in principle, there could be something for this.
Like all the sampling troubles, right? They also have when doing this integration, right? Because you also need to integrate over all the geometrical degrees of freedom to get the StatMech average. So I don't avoid the sampling of the liquid. Or is it somehow easier?
No, that's true. But you can also get cancellation in the degree to which you need to sample, right?
Okay.
So absolutely. And there are huge differences, and that depending on the way you do. Remember, before that we discussed the alternatives for the cycle, right? Yeah. And these are experiments that go more. They would be more in the direction of what you are proposing, that you simply try to directly model the process. Right? Now, you cannot get around this if you are interested in the kinetics and the dynamics, right? Then you actually have to model the process.
True.
But if you only care about the endpoints, then you don't. And then the only argument is really that the absolute endpoints are too difficult to obtain.
Well, but if I care about the actual dynamics, then kind of taking one of those fake dynamic, like non-physical dynamics over kind of phasing in molecules and phasing out, that also doesn't help, right? Because then you're taking some path that is not the actual path that the system could take. So for example, we had this example of some kind of barrier that might not exist if you do the chemical route that might exist otherwise.
Yeah,
so
exactly. Yeah. Yeah, so one has to be very careful, right? And your point is very valid. Also, if and we come to that later also, if all you care about is the energy difference or the differences between two endpoints, right? The direct calculation of those can be much more efficient, right? Nevertheless, the integration of it over the force might give you a new constraint, a new equation, right, for the energy difference, which you might be able to impose as it's like a constraint, right? Where you know this is how the overall manifold of your observable must look like. And what we will also then, of course, later on get to is that if you try to approximate this integral through a Taylor series expansion, other derivative-based methods, right? Then, of course, you also would like to know that actually it's possible to make that connection before you start expanding it. So it's also in that sense, right, that the examples I give, they should serve the purpose of also assuring you that what we are doing is not some spookiness going through non-integer particle systems and so on. All right, thank you so much for raising this point.
No, thanks.
It's very good to clarify this. All right, so the idea of this, basically of this here, right, which you see here, or we discussed, let me scroll back to the, I think we had a couple of equations this year. Right? So it's really this expression, right? Now, this is a very, very general thing, right? It's not restricted to any compound, right? It's not restricted to any kind of conditions. Right? And if you manage to converge things in terms of approximations to the electron correlation, approximation in terms of basis set, finite basis sets, in terms of finite size, a finite number of particles in the periodic boundary sense that you try to model the Avogadro kind of scale, so ergodic theorem basically. Within all these approximations, right? This expression should converge towards the right number. Now there are assumptions like the relativistic effects, right, which we discussed earlier in this course, but also nuclear quantum effects, right? And so I have a paper I'd like to tell you about where we address the nuclear quantum effects And this was then taken up later on by others as well in the field, including Michele Ceiotti and Jiří Janíček at EPFL. Both are at EPFL now by coincidence. So you will see that this is a very general thing, that there are more follow-up papers on this topic, but I just show you the one we wrote. And so the StatMech can be changed to include the nuclear quantum effects by following the formalism of Richard Feynman for path integrals. And so you see this formalism here. We have an effective new potential here, which contains, and this V here, this should be the electronic, sorry, not the electronic, the total potential energy of your system. So this V is the energy that comes out of your DFT calculation, if you wish. And that is the V for a given system. So this arm now is referring to all the coordinates of your atoms. Okay? So this, I apologize, we're changing notation here. This R is not the electronic R. This is the potential energy surface. And now within path integral molecular dynamics, you have to generate multiple replicas of your system. Okay, so for each atom in your system, you now have replica atoms, right? And this is what this index S is indicating. So you're running from 1 up to P replicas of the same system, the same molecule, right? Sitting in the same space. They are basically superimposed, but they don't feel each other, right? So they have no interaction terms, except for this first term in the beginning here. So this is how they interact, these replicas, right? And what you see here is basically a harmonic oscillator between the each atomic coordinate in replica S and its neighboring replica. Right? So what you have is a sort of picture where if you scale out your different replicas, right, in the replica space, right, in real space they are all occupying the same configuration of space. You scale them out, then each atom has a harmonic spring attached to the same atom in its next neighbor replica, right? And so you have these spring beats. So one molecule is oscillating like this to the next, but this one then is coupled to the next, right? So you have a bunch of coupled harmonic oscillators, and they do this in a circle. So this is the most. They're also, you can also open up this chain and then include a nuclear spin and things like this. But for just bosonic approaches, we work with a closed chain, right? These the oscillator strengths, they are related to. They are basically something you can impose to modulate the interaction. So this is something characteristic. Typically, what you have to do is to converge things in the number of these replicas. Right? They are also called beats because for each atom, you can think of this as a chain of beats connected to each other through harmonic springs. Right? So that's the typical classical mechanics example, that you have some beads on a wire, right? And they have some interaction. And so this is also where this comes from. So this number of beads, or this P, has to be converged. At the time, one would have to have 16 or 32 beads. I think some people would even go to 64 beads, implying that your computational cost for getting your QM energy here goes up by the number of beads. Okay. Now, this is an example also of a simulation where you can imagine very neat parallelism on a high performance compute setting, right? So if each DFT calculation is parallelized, right, then you could have on the next level each replica run in parallel on many cores in parallel. Right? So this is what is also known as embarrassingly parallel, because more or less each DFT calculation will require, it's the same molecule, right? It's nearly the same geometry. So they will all require the same sort of time to get to their solution, to get your DFT energy. And so you can really neatly parallelize this. So that allows you to rapidly get those results as long as you have sufficient compute cores available. Now, so this is now your effective potential, and this potential you basically plug into your standard StatMech methodology, right? So you basically have to get the StatMech average. This is the partition function. If you, instead of using your V in here, you use this capital Phi, and voila, you have your nuclear quantum effects taken care of, okay? So it's extremely appealing and attractive to do this. Very, very elegant and so easy, basically. All you have to do is add these replicas and couple them harmonically. Now, there's this C coefficient, which you can show that it looks like this. So it depends on your number of beats here. That's basically it has to be sort of normalized here. Then of course your free energy is simply the logarithm of this partition function, right? And so now we can again integrate this over lambda, no problem. Right? And so this carries through, and then you have to differentiate here your Z with respect to lambda. And then you see this M here, this is the mass of your atom. Now, nuclear quantum effects depend on the mass, right? It's very sensitive to the mass. And this is at the origin of the kinetic isotope effects or isotope effects in general, that you're changing mass and then not only the kinetics, also the energetics changes, and that's reflected in this formalism by this derivative of your mass. Your DFT energy does not depend on mass, right? So what you're left with is this prefactor and this term coming from your harmonic oscillator part, okay? So you need to sample now to get this free energy difference, right? We needed to do a numerical integration here over lambda, and at every lambda, while you sample, you have to calculate your integrand. So in the integrand itself, the QM energy doesn't show up. But of course, in the generation of the trajectory, which allows you to get the integrand, of course, that trajectory requires your QM. So this is something we published 12 years ago in JAX. And there's a movie which at the time we posted on YouTube. Let's see if it's still, yeah, you see it live. So what you see now is for a given lambda value, actually this is not for lambda value, this is, I think this is just one ab initio in the trajectory which is being shown here. But what you can see here are the different replicas, okay? So in each atom, you see actually multiple atoms. I think this is 16 or 32, I don't recall. And these beads interact with each other harmonically, right? Only to their nearest neighbors in the ring, also known as ring polymers. They interact with the other atoms of the same, within the same replica through their DFT QM solution. Right? And so you can run molecular dynamics like this, no problem at all. And you can also nicely analyze, for instance, the average spread of these beads. Indicates, it models the full nuclear wave function, right? And so the spread is an indicator, or is directly proportional to the spread of the nuclear wave function. And so this means the more these beads dissociate from each other, the more they are delocalized, the more these atoms are delocalized. And so as you would expect then, intuitively, the light atoms are more quantum and have a larger spread than the heavy atoms that form the scaffold, okay? So the protons are much more delocalized. And what you can even see is that the protons in the hydrogen bonds are more delocalized than the protons that have no hydrogen bonding, okay? And this is exactly the effect that would result in tunneling of the protons from one side to the other, okay? So this is something which we analyzed and quantified also in this Jack's paper. If you want to look up more of this and look at more references, you will see it there. The technique itself, path integral MD, is quite old. It's very well established. It's part of the advanced curriculum of atomistic simulation. Now, in our case, what we wanted to look at here was in a follow-up paper. We wanted to look at the alchemical change of the mass going from the Zundel cation to its deuteriorated analog. Okay, and so we can change the mass in here, right? And so now you see this integrand. So you see this thing as a function of lambda. Lambda. And this is a snapshot of how this looks like, right? And this is really, if you integrate over this, you get the free energy difference due to change in mass, and that is directly then that is the change. That is the kinetic isotope effect. You can also, and that also connects to Michael's question from before. You can ask the question, we typically would expect from QM and from experience some nonlinear change in your observable, in your force, in your integrand. And so you need to do numerical integration. But that is typically done for linearly interpolating your systems. Right? Now you can ask the question, what if I have a nonlinear interpolation which would linearize my integrand? In that case, evaluation of the gradients at the endpoints would be sufficient to directly predict your free energy difference. And so we also looked at nonlinear changes of the mass and also the potential. In this figure here, it's in the same paper. And you see that also here the integrands behave in smooth fashions, right? We tried different statistics here. It's not so important in the end, but what you can also see is in this nonlinear change, and I believe it was a quadratic polynomial in the mass, you can now get a non-monotonic change in your observable, and this for the mass and this is for the potential. So you can see a very strong effect of, and not surprisingly, right, of changing to a different interpolation function. Now, this relationship between the functional form of your interpolation of the Hamiltonians and the resulting form of your integrand is, as far as I know, is completely understudied. At the time, and I think we cite this paper in here, there was a previous paper by Smith and I think it was Baron Smith, who had looked at improving the sampling efficiency by selecting nonlinear interpolation methods for molecular dynamics, so interpolating force fields. But as far as I know, this was the only paper that was available in the literature that discussed this idea before. And so this quest for finding interpolation functions which would smoothen out your integral, right? Making any interpolation cheaper or making a Taylor expansion converge faster. This quest, to the best of my knowledge, is still completely open and has been hardly tackled by anybody. So a first step in this direction was done in this paper here. In this paper in 2009, I wanted to look at this in more detail. And in particular, I looked at the question of how the HOMO eigenvalue changes as you alchemically interpolate molecular species. Now, these are all isoelectronic molecules. And you can see the geometry here in the panel. Let's start here on the right-hand side. This is the water molecule superimposed with HF. So the fluorine, the heavy atom is always the big one. The fluorine is superimposed with the oxygen, and the hydrogen of HF is superimposed with the hydrogen, or nearly superimposed with the hydrogen on water. Now, this is ammonia superimposed with the water molecule. So here's one water molecule. No, sorry. This is ammonia superimposed with HF. So you see again the hydrogen of HF. And this is ammonia superimposed with the water molecule. Okay. Now, the geometries were relaxed individually, separated, right? So the hydrogens do not superimpose, but only the heavy atom is moved to the same location. And this is now methane superimposed with ammonia, with water, and with HF. What's the other way around? No, hang on. I think this is methane with ammonia, methane with water, methane with HF. This HF sits here. The isosurface plot you see here is the difference in the external potentials. Why? Because by Hellman-Feynman, this is what would be the derivative of your Hamiltonian as a function of lambda. So it's this difference in external potentials. And in front of it, you have a change in electron density, which stems from the fact that you can model your HOMO eigenvalue, as we discussed previously, as a change in energy as you reduce slightly the number of electrons. Okay. So if you do this, then you get a slight change in your electron density, and that's what you see in this bracket. So this is just the corresponding expression for this, right? Now, what you see is that for a linear interpolation of these Hamiltonians, the HOMO eigenvalue changes as shown in this figure. So as you go from HF to CH4, right, there's a strong nonlinear effect. And I think we discussed this before. And this is one of these examples where first order derivative would be qualitatively wrong in predicting the trend. So if you sit on methane and you evaluate the first order derivative for going to HF, the derivative points upward, while in fact the HOMO eigenvalue of HF is below methane. In the inset here, you see a numerical test of the derivative where this derivative is superimposed with the numerical finite difference derivative, which validates once again the Hellman-Feynman theorem for these derivatives. Now, in this paper, and I believe I will still discuss this later on in the course. We also, I looked at this question of imposing nonlinear interpolations. And in particular, rather than using simply this difference here, you could impose a different perturbing Hamiltonian with a different derivative. And so this could then change the shape of your interpolation, making your derivatives more accurate. In this paper, I tried this with a quadratic function. So basically, you inherit one free parameter for your interpolation, right? And I fitted this parameter then to sort of training compound pairs, right? So for each training compound pair, you could then have a free parameter which you fit. And then you can study if this parameter is then transferable to another compound pair. We saw quite some improvement, but I'll come to that later. So this is now something I want to discuss a little bit more in detail. Those of you who are taking right now the course by Guido von Rudolph, which is nearly exclusively on this, right? So he goes into much more detail and gives much more examples. But I will briefly sort of summarize this in terms of papers that have been published using these alchemical derivatives within DFT. And so as we discussed, you can use Hellman-Feynman's theorem for coordinates, for nuclear charges, but you can also use it to directly interpolate entire systems. So this is what you see here. This is not just the derivative for a given nuclear charge, right? This is the derivative for the entire transform, right? And by this inset, you see how this is valid. So you can go directly from methane to HF even though they are not adjacent in the periodic table. There's no problem. I will also show you papers where we have shown that you can also go directly down the columns, right? And if you recall, I also showed you already an interpolation where we went from ammonia to HCl, right? So we are jumping columns and rows in the periodic table. And so all of these results are due to the generalization that we interpolate the entire Hamiltonian and evaluate as a derivative this Hellman-Feynman theorem, just the difference in the Hamiltonians. If they are isoelectronic, the only difference is the difference in the external potentials. All right, let's maybe take a small break and then we'll go into the discussion of these papers. I would say we resume at 9:15. All right, let's continue. I just noticed actually that the non-linearity of the interpolation that I should give some more details on this. So let me just include some more details on the on the paper I just discussed. So I return to the slides. You can see this. Right, so so what you can do is to say that since the path of the interpolation is arbitrary, we pick a different method, right? And of course, you could imagine arbitrarily sophisticated transform functions. Right? You could imagine a transforming field, for instance. Right? This doesn't have to be a scalar scaling function, right? A global scaling function. So in some sense, our linear interpolation in just as one lambda is a very crude thing which you're doing. Right? There could be areas in your system where the changes are very nonlinear, while there are other areas where the changes could be very linear. And so a spatial resolution might be very helpful in order to smoothen out things. But this has not been studied yet. So what at the time seemed to be the first plausible step was to simply go away from the linear interpolation and to presume that there's some scaling function in front of here. This is still a global function, a global scaling function, but it's simply nonlinear. Okay? And in particular, if you impose a quadratic function here, you can show by still meeting the boundary conditions that lambda equals 0 and lambda equals 1, you reach your endpoints. You can show that the function, this f becomes this expression here. where you have lambda, and then there's lambda times 1 minus lambda, so it's quadratic. You have this one free coefficients in the quadratic function. The other two coefficients are defined by these boundary conditions. Right? So it's this one free condition, and you can then use this condition to impose linearity on your observable. In this case, just the energy. I denote this imposed linearity by the L. Right? And so you solve then for this coefficient, and this is the condition which must be met for your condition. If this holds, right, then your energy will be linear. Now, this, of course, contains the information on both endpoints. So for you to make a prediction as to what the other endpoint would be in terms of a first order derivative, this is not very helpful, but we do know the structural form of the equation. Right? So we know how the function looks like, but still it contains information which we would like to predict rather than to presume that we know it already. Also note that for lambda 1/2, this coefficient, which is also a function of lambda, would diverge. So it looks as if your energy would be linear in lambda at the endpoints, but as you approach the middle, right, this is where things go crazy. And so it's a sort of a no free lunch, right? So for integrating, this would be tricky, or for differentiating over it. If you parameterize this coefficient on reference compound pairs, and I denote them here by primes, and I use the same functional form for the homo eigenvalues now, then you can get these coefficients in front of your derivative to estimate the homo eigenvalue at lambda equals 1, using the eigenvalue at lambda equals 0, the derivative for linear interpolation, and then just the multiplication with this reference coefficient. And this reference coefficient I generated by calculating this, this expression for the analog series, only that the one hydrogen, which is present in all 4 species, I replace it by a methyl group, CH3. Okay. So for that series, I then used all these eigenvalues to get the reference coefficients. And then I use these reference coefficients to predict, in this case, you see methane, right? And so from HF, this change, this nonlinear change, then thanks to this information, improves as indicated by this arrow. So these arrows are now the first order derivatives scaled down with this coefficient. Right? And so you see, at least the qualitative trends are right, and in some cases it looks quite good. So this is sort of an indication, right, that we can use we can use reference information throughout compound space, and we can use these nonlinear interpolations to possibly improve our predictions. Okay, with this, I'd like to switch gears now and discuss a different property. Right? So we've discussed various properties, and you can, of course, wonder what are the most important properties. Chemical bonding is certainly one of the key properties for materials and chemistry. Right? And so with Samuel Chang, who was a PhD student in my group, we started to look at covalent bonds and if alchemy can be used to predict them. And one of the first kind of choice systems you can look at is the archetypical chemical bond, is what you would see in H2+. Okay, so H2+ is something you can do analytically, and so it's very much the first thing you should think about when tackling this question. When you do alchemy, though, it really becomes a little bit more tricky, because you actually have 3 nuclei for any lambda value in between 0 and 1. So it's not really H2+, it's something like 3 atoms, 3 non-integer atoms, or H and 2 non-integer atoms plus, right? So they all share an electron. Now, you can see the picture of alchemy here. This is the electron density of your 1 electron, and here you have your 2 nuclei. So this is H2+, right? And then somewhere far away, you recreate the atom, right? So while this atom, this proton gets scaled down in its nuclear charge, here at 0.5, your proton gets scaled up. So we chose a distance of 3 angstrom here. Then at lambda equals 1, your 1 proton was teleported from your equilibrium distance to 3 angstrom. Now, this difference in energy would be a measure of the bond strength, right? So that's what bonds are about, right? You want to measure as a function of the distance how the atoms, how strongly the atoms interact with each other. Now, for this kind of path, right, we can map the energy. So what you see here in black is the true energy for the full curve, just for your reference. In red, you see the prediction of the changes in energy for the first order Hellman-Feynman derivative. And in green, you see the second order prediction for the energy, right? So we see a nice improvement, but you also see that the first order derivative is really not very useful as you change that bond, right? As a function of lambda, right? You see here for a continuous lambda interpolation, the true energy in black, right? So this corresponds to this map here. You see in green, the prediction of the change for second order. Here you see the expansion. And this arrow here, the green between black, this is the arrow which on this map here corresponds to the difference between black and green here. And you see that your linear interpolation here, the red one, goes up so much, it's off the chart for this change. So these are predictions in total energies, right? And so this is a little bit depressing in terms of convergence of the Taylor expansion, right? We would hope that already better lower orders would give you something reasonable, so that the first order is so terribly off is disheartening, if you wish. There's another phenomenon in here which you could notice if you look at this closely, which might be concerning, which is that your black curve here, if you look at this black curve, at the end, is this drop. So this looks worrisome, right? If you Taylor expand here at the beginning of the function, and things look very nice and smooth, but at the end your function does something sudden like this, you can imagine that it will be difficult to capture this effect when you expand around lambda equals 0. So these are two things which one should investigate it. We looked at this closer then in this paper and JCP together with Raghu, Ramakrishnan, and Stenfias. What you see here is again H2+, right? But now we went up to higher orders. And before we discuss the orders, I'd like to also discuss this figure here. So this figure here is the electron density, and it's the same figure as this one, except that we've included more lambda values. And now lambda is this axis. Right? So here at lambda equals 0, you have your diatomic. At lambda equals 1/2, you have what we've shown here, right? It's very smooth. And now at lambda equals 1, you have your diatomic at 3 angstrom. Right? But what you see now is as you approach lambda equals 0 equals 1, the electron, there's only one electron, and the electron will be on the nucleus with the higher nuclear charge. Until really there's perfect symmetry. Only once there's perfect symmetry, the electron doesn't know where to go. But if there's only one electron and your classical charge is higher on one point than somewhere else, that's where the electron is going to be. Right? So this is an interesting scenario. It's a bit exotic, if you wish, right? This is something you will rarely encounter in nature, right? We'd have to set up special experiments for this, but it's definitely possible. This is something that is actually quite well studied also, right? When you look at the dissociation curves of H2+ and H2 and so on. Now the Aaron Cohen in one of his papers also looked at the performance of density functional approximations for such scenarios. Right? And it really seems that it's like a derivative discontinuity in your external potential space that you can go, at least in principle, you can go very, very close to 1 and 1 in nuclear charges. But as long as you're not there, your electron will really be located on the higher nuclear charge. So this seems to be one of these scenarios where the peculiarities of quantum mechanics really show up in quite an ugly fashion. Right? Now, fortunately for us, this scenario where you only have one electron, which has to pick between multiple nuclei, which will always pick just the one with the highest nuclear charge, this kind of scenario is not frequent, right? It's a rare thing. Right? As soon as you have more electrons, they will distribute much more smoothly. So in some sense, it's an artifact due to the sparsity of particles. But this really explains this sudden change, and this explains why, and again, here you see the figure of the predictions as a function of lambda, right? This explains this drop here in the energy as well, right? Because all of a sudden you do gain again a little bit from the delocalization. So you can also show how this is manifested in the HOMO and LUMO eigenvalues as a function of lambda. This is what you see here, the HOMO-LUMO eigenvalue as a function of lambda, and you see that basically this looks as if you have a surface crossing. And so it could very well be that in terms of a Taylor expansion, you're actually predicting something like the HOMO, and after the crossing, the HOMO became a LUMO. So you have a state crossing, and if you have an expansion here, a Taylor expansion, you're rather predicting this red triangle than the green triangle, right? So within your perturbation theory, the state you're predicting is, of course, the same electronic state in which you expand, right? And if on the way of your transform there was some state crossing, your reference system does not know about that, and so you're predicting. You could be predicting observables of excited states while expanding in your at lambda equals 0 in the ground state. Now, also this aspect of alchemical interpolations, namely state crossing and excited states alchemy, has not yet been studied. What you also see here in this figure now, to complete this, is again the first order prediction, the second order prediction you've also seen. Now you see the third order and the fourth order prediction, and you see something that is also quite concerning, which is that it does not look as if it converges. There seems to be rather some divergence, and so second order seems to be sort of the best possible guess in practice. Similarly, here you see your divergence of these terms, with second order being the best estimate. So as a function of order, you see here the error you're making for predicting the H2 plus at distance 3, and you see it does not converge, right? So third and fourth order are worse than second order. So now at the moment we believe that this has to do with the particularity of dealing with just one electron, and that the convergence of these alchemical expansions, these convergence properties for many electron systems are much better behaved. But it's not yet proven that, so mathematically has not yet been proven under which circumstances things converge and when they do not converge. So, of course, things also in these perturbation approaches, they are supposed to converge for infinitesimally small perturbations. Right? So this trade-off between convergence versus radius of convergence versus size of perturbation. This is a very interesting Pareto front, and as far as we know, it hasn't been established yet. In this paper, we pushed things further beyond H2 plus. So H2 plus is a toy system, right? And in particular, we considered the single covalent bond in systems with 10 valence electrons, right? So think of the HF bond or CH bond and methane, these kind of systems. And when you look at this bond, then the bond energy is really a relative energy, right? So any bond energy you would be free to choose some reference point, and then you say, okay, I'm going to measure the strength of the bond with respect to that energy, right? So you can set your minimum to 0, as shown here, or you set the dissociated atoms to 0. But in any case, it's this difference in energy between two geometries, right? And so that's what you have here, D0, right? That's your reference distance. And you look at this energy difference as a function of the distance. Now, this means that you can write it like this. It's the difference between these two Hamiltonians, and we can now interpolate alchemically at two distances, once at your reference distance, and then for all the various Ds at your query distance, right? And you interpolate from your reference system to your target system. So let's look at HF to HBr. So this is HBr here. I'll show more in a minute. But you can see here a change in electron density for such a change in the alchemical system. And this is at the equilibrium distance, and this is at some optimal distance. So the question of what should be this D0 is an open question. And we basically took this D0 as something we can calibrate, okay? So we find the D0 at which your alchemical prediction of the bonding curve is the best. And so if you choose your D0 to correspond to the equilibrium distance, these are the changes in electron density. If you choose it to be some optimal value, for instance, 2 angstrom, then you can see for such a change a much smoother change in electron density, indicating a better convergence property of the Taylor expansion. So here you see now some numerical results for this. Let me start with this column here. We're predicting from HBr the energy, the bond curve of HCl and HF. Okay. And you always have 3 curves in here. The true curve, which is in black, that's the one that's not being predicted. That's the reference, right? Ideally, that would be the target, right? Ideally, the predicted curves are exactly on the black one. The red curve is the first order prediction, so first order alchemy prediction, and the blue one is first and second order. You see this, we can do this for every column in the periodic table. Right? And these are what we call vertical predictions, meaning that the reference Hamiltonian and your target Hamiltonian have the exact same geometry. So you see now the predictions using this row here as a reference, right? For making predictions on HCl and HF. And you see very encouragingly, the second row here has very good agreement for first and second order. And the first row here has better prediction for second order than for first order. That's nice to have that as a trend. But you also see qualitatively, they all have a nice minimum and it looks quite reasonable. Right? So these errors we are making here are not on the scale of 100%, but some fraction. Now we can repeat this game by making the second row our reference and by making the first row our reference. Okay. So we are changing target to reference, right? We can do all possible combinations. And so you can see varying predictive power, right? So one thing you can see is as we go from this third to the second, very good predictive power. If we go to the analog, the first row to the second, worse predictive power. Now, this is something we can interpret and understand. What's happening here is that your minima, right, they are further outside. Right? If you compare third to second, the minima are very close to each other. Right? They're very similar. Here they are not. Right? One of the reasons is that in the first row, you have elements which are much smaller. And as you go to second row, their core radius has to grow, right? And correspondingly, their valence electron radius grows dramatically. And to predict this with alchemy is, of course, harder than when going from third row to second row, where the change in your core is much less dramatic, and the change in your equilibrium distance in the bond is much less dramatic. If we go to the middle case, right, we can see this rationalization of these results confirmed. What you see here is that if we choose the middle row as a reference, it's harder to predict the first row than it is to predict the third row. Right? Again, suggesting that second and third row are much closer in terms of a perturbation than second and first row. Now, this vicinity, right, this measure of similarity in terms of size of the perturbation, it's extremely interesting because formally in terms of nuclear charge or in terms of the periodic table distance, right, they are the same, right? They are the same distance. But of course, the change in the chemical in the core electrons, right, as you go from first to second row, is much more dramatic. You go from having from 2p, you go to 3p, right? So this is a whole new shell which then opens up for the 3d electrons, which don't exist in 2p, in 2 on the second level. Right? There are no d electrons. And so these d electrons are also present then as you go to the fourth, to 4p in the third row here. And so the rate at which your nucleus expands, right, is much more dramatic in the beginning of the periodic table than later on. So this is how we can understand these changes. Now, what we note, however, is that for in between second and third row, your predictive accuracy is extremely high, and already at first order kind of derivatives. What we also note is that if we go upward from third to first, or from second to first, your second order perturbation improves things. By contrast, when we go downward from first row to second, and also from second to third, the second order perturbation makes the things worse, makes predictions worse. Right? So again, this connects to what we already discussed before, the convergence of your Taylor expansion. You should not take it for given, right? Or the systematic improvement with the order, right? Things can oscillate, right? And it can be that your next highest order is worse than the previous one. Now, we also tested this, these predictions on on double bonds, right? As well as triple bonds. And you can do this by looking at something like this here. So what you have now is this is still a single bond, but we are taking the column, the fourth column, right? This is column 4 in the periodic table, together with the column 7 for the halogens, right? So these are single bonds. We take this single bond now to predict the single bond as you go up or down the column for the silane group or for the halogen. Right? So these are different combinations now of single bonds. And this is sort of the one from our previous results, where overall you would expect best predictive power. And again, you see as we go downward, so these are these cases, right? These are the downward cases. If one of them goes downward or both, right, your predictive power is typically pretty good. Now, going upward, things can be more problematic, right? So you see the predictive power is not as good. The worst you can do is go up and down. So if you go up and down here, or if you can go up and down here, you see you have the worst prediction. If you go down with both, you still get some decent prediction with first order. And sort of diverging results you get if both groups go up. Now, you can do this for the double bond. So this would be group 4 and group 6 elements. And for the triple bond with group 4 and group 5 elements. Again, you see similar behavior. Typically, as if you go upward, your predictions are worse than going downward. So we as a result, right, we have some mixed messages. Right? So in some cases, second order alchemy does not seem to improve things. Right? And the deviation can be quite substantial. Right? So you see, so on the, you see here, if you presume your well to sort of converge, this error might be on the order of 1/3 of the well or something. Right? So this is still qualitatively, it's okay, but it's not something you would like to bet on, right? However, here there are cases, right, where the red predictions, so first order predictions, can be extremely accurate. Right? This is very, very accurate prediction of binding. Right? It's really a little bit of a question. How bad can it be? How good can it be? Now, we used one parameter, right, to if you wish, as a calibration, right, and this is this D0, this D-opt, right? And it turns out that this D-opt has some cause relation with the equilibrium distance of your target function. Right? So here you see a scatter plot of D-opt versus the target's equilibrium distance. And this is a pretty decent correlation. The root mean square error is 0.15, and you should take 3/4 of the equilibrium distance and add 1 angstrom to it to get a decent shot of a d-opt. And this seems to hold no matter what is the order of your Taylor expansion. So we looked at all the possible combinations here. Now, to estimate the equilibrium distance of your target, you might think that this requires prior knowledge about your target. This in principle, that's true, of course, but typically it's much easier to predict decent geometries than to predict decent energies. So oftentimes a force field or some semi-empirical approach will get you already very decent equilibrium distances, right? At negligible cost. So you can use that as an equilibrium distance here to calculate your d-opt for your alchemical prediction, which then can give you a very accurate energy. Or it can also give you a poor estimate, right? So it really depends, as you can see here, on the various combinations. But usually, as we said before, when we are talking about changes between the second and the third row here, your predictions are quite accurate. So one question would be, how accurate can it really be? If we wanted to look at the best possible prediction, what is the best, the most accurate estimate you could ever hope for? And so we looked here at predicting Hbr based on HCl or predicting HCl based on Hbr. So these are the binding curves, and we also have some references here. So the prediction, the alchemical prediction now is made using the PB0 function, which is a more sophisticated density function, right? And the true HCl energy is shown by these black circles, right? So HCl is the lower curve, Hbr is the higher curve. That's the true HCl. And now if you predict HCl using Hbr, you would get these black squares here. The red squares here. So you see this here, right? It's pretty good. If you use the PBE function to calculate HCl, you would get the green diamond, right? So the alchemical prediction of HCl at the PB0 level is as good or even slightly better than a GGA approximation of HCl. Yeah. So it's on the order of differences in density function. Now what about Hbr? So the Hbr curve is here, right? The black filled circles. If you calculate Hbr with the PBE function, you see the filled green diamonds. Right? If you calculate Hbr with first order perturbation theory on PBE0, you get the red squares. Yeah. So in this case, it's even more clear that the first order alchemy is much more accurate than the GGA. Now, there's another bunch of results here shown as this dashed black line. And these are couple cluster results, if I recall correctly, or MP2, I don't remember exactly. But these are even more accurate than your PB0. And so you see that also between PB0, so for HCl, you see the deviation. You see that also when going through the various approximations in quantum chemistry, different functionals, post-Hartree-Fock methods, alchemical predictions can be on par with that sort of variance you would expect. Okay. Now,
maybe just to understand that a bit better, because that looks pretty cool. So just to understand, so for example, for the Hbr curve, there has basically not been done a single Hbr calculation. It's all HCl and then extrapolating from there using derivatives and Taylor expansion.
Yes. So this is, it's all this formula, right?
And it has all been done at a fixed distance or along the entire curve and then extrapolating from there?
No. So these are vertical predictions, right? So you evaluate the alchemical derivative at every distance here.
Got it. So you have basically a full HCl curve, and from there you vertically predict upwards towards the Hbr.
Yeah.
Cool.
Yeah. So the question of varying not only the composition but also the geometry, right? These are two independent variables. Now, of course, you can fold them both together, right? But we are looking here only at the contribution coming from the changes in the composition, separating it from the geometrical effects. So we call this a vertical prediction. Now, this is, of course, I have to caution you, right? This is the best possible case, right?
Okay.
I'm super cherry picking here. Do not presume that alchemy is as accurate as that in general. As you see in these curves, right? If you go upward, your predictions can be horrible. So if we have a better understanding under which conditions we can expect alchemy to be predictive, right? Then it might really turn into something very useful. Now, so far I've mostly discussed molecules and so on. I also want to tell you about the possibility to bring this to crystals, right? This is quantum mechanics. It works everywhere. And the same sort of exercise we have been doing with Alisa Solovyeva, who was a postdoc in my group, on crystals. And in particular, we looked at the Alkali halide crystals, so potassium chloride, sodium chloride, all possible alkali atoms and halogens. And these crystals typically occur in three different kind of unit cells, crystal unit cells. They consist of FCC, BCC, or zinc blend. Okay, and so these different crystals, they have their minima in very different lattice constants. And if we want to map them all, it can be tricky. But here you see always two crystals present in a given unit cell. So this curve here, down here, is the energy of the sodium chloride in the FCC unit cell as a function of the lattice constant. And this up here is the energy of the BCC unit cell of sodium chloride. Here you see, again, this curve is the same as this one, but now you see it with the energy of zinc blende. And you see this zinc blende lives on a slightly different scale than the BCC. So this shape changes now. It's basically like a zoom in, right? And then in this last column here, you see zinc blende and BCC, and you see their relative minima again. Okay. So zinc blende is basically in between BCC and FCC. Right? There will be some curve here. What we did now is to look at the energy difference between these guys as you go from sodium chloride to potassium chloride, right? And the corresponding curves in the same crystal units, right, are shown here for potassium chloride. Right? So this potassium chloride in the BCC, potassium chloride in the FCC. Here you see potassium chloride in zinc blende, and here in FCC, and here you see it in BCC, and here in zinc blende. These vertical dashed lines, they indicate the minima of these systems, right? So this is the minimum of FCC and potassium chloride. This is the minimum of FCC and sodium chloride, right? So these are just meant to guide your eyes. And now we come to the alchemical prediction of we predict potassium chloride using sodium chloride as a reference, okay? And these are just vertical predictions. They live on the same unit set, right? On the same lattice constant. And so what you see here now is, of course, horrible absolute energies, right? So the energy scale here is not meaningful, right? But you see, if you compare your potassium chloride curves of BCC and FCC lattice, you can hardly distinguish them from the true curves. Same holds for zinc blende and FCC, and for BCC and zinc blende, right? So the relative energies between these two crystal forms is very well predicted by first order prediction. It's a first order alchemy prediction. So if you have lattice constants of sodium chloride, lattice constant scans of sodium chloride in the various possible crystalline forms, doing the alchemical predictions, you get the lattice scans for other crystals in the same unit cells for free. The relative energies of them for free. Okay, so in this table, you now see the kind of data deluge in chemical compound space, which you can imagine, right? So this is an archetypical example, all possible references versus all possible targets. We have, in terms of halogen, fluorine, chlorine, bromine, iodine, and you have all alkali atoms. Right? And in each combination, you have three lattice constants, three unit symmetries, crystal symmetries you can predict, FCC, zinc blende, and BCC. And you can, of course, also include the true curve, true curves, how it should be, right? So these are typically, I think we report them on the diagonal here. On the diagonal, you have the true one, and we are using these to predict these, right? So it's a symmetric matrix. Sorry, the entries are not symmetric, but the indices are the same, right? So to better clarify this, here you have a zoom in, right? We are predicting these crystals, starting with these, right? And you can now, because if you recall, right, look at the location of the predicted minima. You cannot distinguish this, right? So this is substantial change in lattice constants, right? Going from sodium chloride FCC to potassium chloride FCC. Just by doing the first order derivative, you know where the minimum is for potassium chloride. Right? So this is one of the properties you want to look at, right? So lattice constants, you might want to look at energy differences, or even at bulk moduli. That's the curvature of your potential, right? And so you predict from this is one reference. If you predict all these other crystals, you see here the errors for the different lattice constants in angstrom. Here you see the energy differences in milli-eV. These are very small numbers, right? It's amazing. This is the largest, 66 here, but And these are predictions of the bulk module. What you see in these rows here is how difficult it is to predict this target, right? How hard is it to predict potassium chloride, let's say, right? You see on average, it's easier to predict potassium chloride than to predict sodium chloride, right? And again, on average, it's easier to predict rubidium and then cesium. So sodium is the highest up in the periodic table, right? So what we saw also for the covalent bonds, right? Predictions of the first row are harder because those chemistries are more dissimilar than the chemistries in the later elements, right? So these numerical results would suggest that interpolations in chemical compound space are easier among late elements in the periodic table. As far as I know, this statement has not been made in the literature. So here's just to highlight some energies. This is sort of chemical accuracy. Right? And remember, this is all just first order differences. Now, why would you care about the differences between in energies between different crystal structures? One of the reasons is that as you go from something like sodium chloride to cesium chloride, actually the ground state energy of the crystal structure changes. Right? So the one, I always forget which one, FCC or BCC, one of them is favorable in one or the other, right? And so it means that you basically have a different aggregation state as you change, and you can do this for a mixture of these crystals. So for binary mixture of sodium chloride to cesium chloride, you would observe such a change in aggregation state. So in this paper, we also discuss such mixtures, but I don't include them here. But you can basically imagine this kind of matrix now in terms of mole fractions of all the possible mixtures. Right? Okay, I see it's 10:15. Are there any questions so far? Okay, let's maybe take a short break of 5 minutes or so, or let's say 7 minutes, and we proceed at 10:20. Okay. All right, let's continue. So we've seen the applicability now of alchemy to homo eigenvalues, to kinetic, to nuclear quantum effects, to force fields, to melting points, to covalent bonding and single, double, triple bonds, to crystalline systems. I now want to tell you still about a couple of applications, in particular related to metal surfaces and the band gap problem in crystals. And then I'd like to very briefly discuss a more recent paper on second order alchemy, which then should lead to the next homework I'd like to give to you. So let me share again the file, the slides. So this was a paper by a PhD student from another group who wanted to test the applicability of alchemical predictions for DFT-based estimates of volume, so related to equilibrium lattice constants and various metals. And so in particular, these D group elements, which he considered here. So these are adjacent and nuclear charge, right? Zirconium, niobium, molybdenum, technetium, ruthenium, rhodium, palladium, and silver. And you see the volumes in FCC and BCC. In black, you see the GGA-based prediction, right? The black diamonds. And then the blue triangles are either when you predict to the left, you get a pointed triangle to the left. When you predict to the right, you get a pointed triangle to the right, okay? And so you see the predictions always left and right. He also did some testing on improving the GGA, but you can ignore the green one, the red circles. But you see very nicely the alchemical predictions trace the volume of the volume trends in FCC and BCC for all these metals. Okay. So now you've seen main group elements, small molecules, crystals, alkali, halogens, metals, D elements, right? So this really amounts to numerical evidence that this approach is general, right? Now, I'd like to briefly still discuss papers not from my lab, but from John Keith's lab. John Keith is at the University of Pittsburgh, and he's interested in studying heterogeneous catalysis. Okay, so you have a surface, and there's some reaction happening on the surface, and the question is how can we modify or improve the surface such that the catalytic process is improved? Very much similar in spirit as the work of Norskov, which I also mentioned in the beginning of the course. And so one of the key properties for estimating catalytic activity is the adsorption binding energy. And so his question was, if we have some binding energy of a reference alloy, can we predict, of a reference compound, a reference surface, can we predict the binding energy of a target alloy, a query alloy, using first order derivatives, right, of the binding energy, of changes in binding energy due to change in chemical composition in the surface. And so basically, he proposed this procedure. You first calculate the reference binding energy using a geometrically related structure from DFT. So you have your slab and then your molecules and some adsorption. And then you get the relative alchemical potentials, right? In terms of differences of electrostatic potentials, we discussed this earlier. This is the alchemical nuclear potential. So it's the electrostatic potential at the nucleus, right? So you can calculate those, and then you test hypothetical alloys by making these isoelectronic transmutations correspondingly, and you estimate then the free energy. You calculate the derivative of the binding energy using this delta mu, so the changes in this chemical potential, and with this you estimate the change in binding energy. And so how well does this work? Here's a scatter plot where you predict the changes in binding energy using alchemy and changes in the actual, this truth versus prediction, right? Now notice scatter plots should always be on squared figures, right? So that it's easy, that it's trivial. The diagonal is the perfect prediction. You can easily then project multiple predictions onto each other just using different colors. In this case, these correspond to different adsorbing molecules, OOH, just oxygen, or OH. And you can also consider surface and skin kind of scenarios of binding. So these are mixed here with different errors that are being made. On the platinum slab, the palladium slab, and the nickel slab, and these are now alloys that are being mixed into these slabs, right? But this is the base lattice on which this is happening. And you see very nice correlations, right? And this is an EV, right? So this energy scale is quite substantial, right? So we cover a wide range, and you can see that the first order derivatives, again, for such a relative energy, right? For the adsorption energy is quite predictive. And then you can discuss trends among these as a function of how many atoms have been mutated, how much does the error increase. And the more atoms you mutate, the larger your perturbation, the larger the error you make. Right? So this shouldn't be too surprising. You also see here some mean absolute errors in binding energies associated with different sites. So you can analyze where in the lattice, right, you inherit larger errors for the different combinations of adsorbates and metals. With this, I'd like to change to another paper where we looked at the band gap. And in particular, actually, we made prediction for the entire band structure. Right? So this was Samuel Chang's last paper of his PhD. And he predicted for any band I, he predicted for any K points, right? He predicted the band from an alchemical reference, so for new chemical composition at K, so reciprocal space. He used as a reference some other chemical composition at the same K, plus the first order derivative of that eigenvalue. And he evaluated that eigenvalue. You remember I talked about HOMO eigenvalues by varying number of electrons. In his case, he simply took the molecular orbital and took that expectation value, right? Because the perturbation expression also works for single particle, for the single particle picture, such as the Kohn-Sham orbitals. You can also simply use the Hermann-Feynman theorem, and therefore this works as well. And so you can get the derivative like this. Right? So if you have the molecular orbitals, you just evaluate the difference in pseudopotential. And he revisited this system which Alex Zunger had used. You remember the paper we talked about in 1999. In particular, he looked at gallium arsenide and aluminum arsenide. What you see here now are two predictions. In blue, you see the prediction of aluminum arsenide using gallium arsenide as a reference. And you see the entire band structure, and you see the true. The true is shown in black, the truth. And similarly, down here, you see the prediction of gallium arsenide using aluminum arsenide as a reference. Right? And you can see the band structures look very similar. It's very difficult to distinguish the prediction from truth. And so not surprisingly, if you do a scatter plot of truth versus prediction, you see a very good correlation. You see also that when you predict aluminum arsenide from gallium, or if you predict gallium from arsenide, from aluminum. The error is not the same, but there seems to be sort of a reflection symmetry, right? It could be that there's still some very easy correction method if you can calibrate this remaining symmetry, especially for the lower line bands, right? So this is an interesting finding, right? The core electrons here, they seem to be very well behaved. Only as you go up to the higher to this is conduction band, right? Then things are getting all garbled up. All right, so we made various predictions then of the band gap and the various errors, the various eigenvalues, the various levels. And here you see some statistics. If you plot the error for the reference showing here versus the prediction, right? And you see the smallest errors again are among the late elements, right? You see this for the 3-5 as well as for 4-4 semiconductors. So we didn't only look at these, but also at those. I will revisit this paper later on in the course as an example of a design application as well. So based on these predictions, we also then use the genetic algorithm to identify the best mixture of gallium aluminum arsenide to maximize the band gap. But I'll show that later on in this course when we come to the examples. We also predicted alchemically changes in crystal structure stability. And this was for H2 adsorption energies in crystals of these stoichiometries here. So these are stoichiometries which have very many different crystal structures that are competing in energy. And you see here a ranking of the crystal structures. And we use this as a reference, the calcium dyes, to predict the strontium dyes, right? And vice versa, predict using the strontium dyes to predict the calcium dyes, right? And you see that, so in the middle, you see the prediction, and here you see the truth. And you see that the ranking of the crystal structures is typically, so it's not perfect, right? Here you see the ranking being messed up, but here the top one is predicted correctly in either cases. And so you can see the errors of the ranks, the distribution you can see here. So you get a clear maximum on 0 errors in the rank. And then I mean, it's not perfect, but it's still useful. With this, I'd like to come back to the second order derivatives, right? This is now a paper which we published in 2019 with Stan Fier as a collaborator of mine, as the first author. And we wanted to look more systematically at second order contributions in chemical compound space, as shown as here. So number of electrons versus atomic configurations versus nuclear charges. And in particular, we looked at the second order derivatives. And this is what you see in your Taylor expansion here as this term. So you can write it down in this matrix notation if you wish. And now our X includes all degrees of freedom. So nuclear charges, coordinates, and number of electrons, okay? And in this entire space, you can then write down the Hessian as the second order derivative matrix, and various components of this Hessian we already discussed in this course, right? So the first component is the alchemical hardness. So this is the nuclear, the second order derivative with respect to nuclear charges. This we mentioned already in the grand canonical ensemble paper, and also the electronic hardness, right? This is also something we discussed already. This diagonal term here, the nuclear coordinates, this is the conventional vibrational Hessian. Right? So that is a subset of this. And then you have these three elements, which are less discussed in the literature. One is the mixed second order of nuclear charges and coordinates. We call that the alchemical force. One is the second order derivative of number of electrons with respect to nuclear charges. So the derivative with respect to number of electrons is the HOMO or the LUMO. So these are this alchemical Fukui function here, which we discussed also before. This is something which is related to alchemical changes of HOMO-LUMO eigenvectors. And then also, of course, you have this term. This is known as the nuclear Fukui function. This changes coordinates and number of electrons. So basically how your HOMO or LUMO eigenvalues change as you change your coordinates. This does not include changes in chemical composition, right? So you can diagonalize this Hessian, right? And then you have the coefficients, the eigenvectors of this Hessian, together with the eigenvalues, would amount to your second order derivative. And this diagonalization, of course, for vibrational modes is done to create these iconic molecular vibrations, right, which you're all familiar with. But for nuclear degrees of freedom, this hasn't been done yet, right? And so here you see an example of such a change in nuclear charges, which we proposed in this paper, or which we plotted in this paper. You see the electronic energy here as a function of the distance between the two atoms. And here you see changes in nuclear charges. These are all isoelectronic, right? Now you can make predictions, right, to first and second order, to the left and the right. So if you start from N2, you have a left or right hand prediction, and the error you will make in your prediction is the same, right? You're on the top of this hill, either you go to the right or the left, so your error will be the same in second order. Now, if you make a prediction from CO, either to the right or the left, you will make a different error. Okay? It's no longer symmetric, and so there's a larger error. As you go further, the error grows even more. At some point, you start populating. You leave the P shell empties, and you're in the S shell only. Now the alchemical normal modes then correspond to the diagonalized eigenvectors in a space like this, where you can go to the left or the right, starting from N2. You go to oxygen or carbon by adding or removing more protons. By doing these changes on this axis here, you do not introduce charge, while on this axis you do introduce charge. What you see highlighted here in red and blue, or in red blue, blue red, are these two orthogonal normal modes that would diagonalize your changes in Z. So for these two degrees of freedom, right? So it's this 2x2 matrix here you see them. The corresponding eigenvalues are shown here for these two normal modes, right? I would like to ask you now as a homework to to show that the second order derivatives here on the top of the ridge, right? These are the first derivatives which should not vanish in the z dimension, right? So your first order derivative must vanish here. And I'd like you to show that this has to be the case using basically the Hellman-Feynman theorem. So how does the fact that this is a maximum here with vanishing gradient, if you are on N2, how is this fact manifested in the Hellman-Feynman theorem? And actually, this will hold for any homodiatomic which changes nuclear composition in a charge neutral and isoprotonic way. Right? So this is the homework, and with this I'd like to conclude for today. And if there are no further questions, then I'd like to thank you for your attention, and I'll see you next week.